Okay, this question. Uh, Give one example of alkene where addition of the HBr gives same product in the presence and the absence of peroxide. Presence and the absence of peroxide means presence means it is a anti-Markovnikov's reaction, and in the absence of peroxide means it is Markovnikov's reaction. So I will write about the Markovnikov's reaction. M dot R I'll write. I'll just write this short form because we have to do many questions. Markovnikov's reaction. Or I'll write this full form. Markovnikov's reaction. The negative part, okay, what I'll say is that a rule of this is that Markovnikov's reaction is this is Markovnikov's means in the absence of peroxide, absence of peroxide. So negative part of not part, negative part of adding species goes to that carbon to that carbon in alkene to that carbon in alkene which is having least number of hydrogen atom. So this is a rule. There is a theory behind it. There is whole mechanism for that. I'll not discuss that mechanism here, but I'll tell you the rule. Means if it is this alkene CH3, CH, and CH2. Negative part will go to the carbon which has less number of hydrogen. Okay, and the positive part will go to this. Means if we are adding a HBr, this is in the absence of peroxide. So negative is Br minus, this Br minus is negative. So it will go over here. You are going to get it this way, CH, Br, and this is CH2, no? One hydrogen you connect to this. This will become CH3. This is a addition reaction. This is actually example of a addition reaction. Double bond is changing to what? A single bond. Right? This is in the presence of the peroxide. Sorry, in the absence of peroxide. So in the absence of this is in the absence of peroxide. In the presence of peroxide, in or I'll write anti-Markovnikov's anti-Markovnikov's reaction. In the presence of peroxide. So this is CH3. What does this rule says? Rule is opposite. Opposite means negative will go to the carbon which has more number of hydrogen in a carbon-carbon double bond. Negative part will go, negative part of adding species. Negative part of adding species will go to the carbon which is having more number of hydrogen in carbon-carbon double bond. Means if this is your alkene, this is CH, CH2, you add HBr and you put H2O2 or any peroxide, benzoyl peroxide, H2O2, this kind of thing. So product will be what? Negative will be here on this carbon and hydrogen will be over here. Means the product will be this way: CH3, CH2, CH2, Br. This will be your product, right? So based on this, so question asked is this was a revision of the whole Markovnikov's and then anti-Markovnikov's reaction. Let's understand the question. Give one example of the alkene where addition of the alkene and so you have to take a symmetric alkene. For this question, answer is very simple. It is symmetric alkene. You take a alkene like this, CH3, CH2, CH. Yeah, this is a symmetric alkene. More examples, CH3, CH2, CH, double bond, CH2. This is another example. So these are more examples you can derive. So this is a kind of symmetric alkene. We call this to be a symmetric alkene. So next, you do this in the presence of peroxide H2O. Sorry, not H2O2. We'll do without a peroxide HBr. The product Br getting substituted here. Let's do this. CH3, CH, Br, CH2, CH3. It is very simple. Br getting substituted here on this carbon or here, and hydrogen getting here or here. It is one and same. No, you are going to get the same product, right? So let's not worry about this. Even in the presence of the peroxide, even if it is in the presence of peroxide, what's going to happen? Peroxide means what? H2O2. What's going to happen over here? Same, no? Means let's say you are getting this product in the absence of peroxide. So you are expecting opposite product in the presence of peroxide. You are expecting this, but both the products are same. Name of this is what? 2-bromo butane, and name of this is also 2-bromo butane. So answer is any symmetric alkene. Give one example. So answer is over here. It could be a but 2 in, or it could be um, hex 3 in. Hex 3 in is this. Hex 3 in is this. CH3, CH2. This is hex 3 in. These are going to show you compounds like this. Write a chemical reaction to depict the preparation of haloalkane or haloarine from each of the following. First is ethyl alcohol. Means if you see in the NCRT, while understanding the haloalkane haloarine, first reaction preparation of the alcohol, ethyl alcohol. Ethyl alcohol is this: CH3, CH2, OH. This is the ethyl alcohol. You'll be adding a acid like HCl, and the reagent is what? ZnCl2. This gives me a alcohol. This gives me a alkyl halide this way, Cl. Plus water will be less lost over here. So this is the first reaction. Second is preparation of haloalkene or a haloarine. Toluene they have given. Toluene, if it is the case, toluene, you can either do for a question number preparation of from toluene if you are preparing. You can prepare two kinds of alcohol. Sorry, alkyl halide. If it is a toluene, toluene is this, right? Toluene is this. Either you can do this. You can get after chlorination. You can get this. Understand the difference, huh? You can get this. You can substitute Cl over here, or you can do substitution over here. Okay, this is haloalkane, and this is chlorine. Huh? This is haloarine. How this is achieved? This is achieved by, we have done this one kind of reaction. This is electrophilic aromatic substitution. Okay, here also this is also chlorination, and this reaction is achieved by free radical halogenation. Free radical halogenation. Okay, if you are doing free radical halogenation, chlorine will never get substituted here. If you are doing a electrophilic aromatic substitution, means electrophilic aromatic substitution means what? Reagents will be what? A chlorine plus Fe. Cl3. Here it is what? Chlorine and a UV light. Understand this difference, What is asked? Is it a free radical halogenation is asked or a electrophilic aromatic substitution? So hello alkane. Here this is haloalkane and this is haloarene. That's it. Next is aniline. Okay, let's start with this. I'll clean this part. Just make a note of these things. I'm clearing this. Aniline. For the option C, that is aniline, what we'll be using is Sandmeyer's reaction. Sandmeyer's Meyer's reaction. Sandmeyer reaction is what? We start with the primary aromatic amine. Primary aromatic amine is aniline, no? This is NH2. This is aniline. Okay. It is reacted with a nitrous acid, HNO2. Okay, this is nitrous acid. What it gives you is this N2 plus Cl minus. This is called as benzene diazonium salt. See, it's very simple how to remember this reaction. This is a step one of a Sandmeyer reaction. This is a step one of the Sandmeyer's reaction. And what you are preparing over here is a haloarene. You are preparing a haloarene. So this is benzene diazonium salt. See, this is a acid. Understand the difference. This is a acid and this is a base. Whenever base and acid reacts, what do you get? You get a salt. This is a basic thing what we learn from the 9th, 10th standard. When base and acid reacts, what you get is salt. Why this is basic? Because this is a Lewis base. It is capable of donating these electrons. That's why this is a base. This is HNO2 and HNO2 is a acid, a good acid. So see, instead of this HNO2, no HNO2, they can also write NaNO2. Don't get confused with this NaNO2 and HCl. This also and this writing this HNO2 and NaNO2 is also a one and same. This is in situ reaction. In situ reaction means this HNO2 is prepared. This HNO2 prepared. HNO2 is prepared in reaction mixture only. In reaction mixture during reaction. During reaction only. Means you take this NaNO2, NaNO2 and HCl. What you get is HNO2 and a NaCl. Right? Even writing this or this is one and same. Finally, you are getting HNO2. Then HNO2 will react with this. So this is the first step of Sandmeyer's reaction. I'll clean this red part. Just make a note of all these things. I'll write a step 2 because our haloarene is not prepared. Right? That is what we are preparing. So step 2 is this. Step 2, there may be some variation depending upon what kind of halide haloarene you want. Whether it is chlorobromine, chloroarene or a bromoarene or a iodoarene. Fluoroarene we don't prepare by this method, right? So if it is, let's take this benzene diazonium salts, right? This is N. See, diazonium salt it is this way actually. Nitrogen triple bond and a nitrogen. This nitrogen is forming four bonds or not. Whenever nitrogen forms a four bond, it has a positive charge. And this is like a counter ion to this. Cl minus is the counter ion of this. Like we write a NaCl plus and minus. That is what it is. So this bond is very, very weak. This bond is very, very weak. So if in the presence of CuCl2, Cu2Cl2 or CuCl, what you get is direct substitution. Otherwise, substitution is not that easy on a benzene. You will get C. Or if it is this N2 plus Cl minus, understand? or if it is this. Step 2 possibility is that if it is this nitrogen triple bond plus and Cl minus plus Cu2Br2 or CuBr. This is going to give you a bromoarine, okay, or a bromobenzene. This is chlorobenzene, right? This is bromobenzene. And if it is this potassium iodide, just potassium iodide for the preparation of the iodobenzene. This is iodobenzene, right? This thing is coming here. So this was the answer for all these three, right? Three options. First, the propene. Do the Markovnikov's reaction. You will get the answer. We have done this in the previous question. Do Markovnikov's reaction. Markovnikov's reaction. That's it. Okay. Next question is question. Arrange the following compounds in the increasing order of their boiling points. Increasing order of the boiling point. See, boiling point. One thing is that boiling point is you can rate directly proportional. Many factors are there, hydrogen bond, this, that, then many factors are there. But boiling point in this case we can say is directly proportional to molar mass. Molar mass. And if molar mass, since these are isomers, they are related by isomers, molar mass will be same. So boiling point, I'll write isomers is inversely proportional to the branching. More is the branching, less is the boiling point. Since all these three are isomer, which is having maximum branching, option 3 is having maximum branching, so it will have least boiling point. This compound will have least boiling point. Then one will have the little higher boiling point, and maximum will be in option 2. That's it. Increasing was asked. Okay, this question. Draw the structures of the major mono-halo product in each of the following reactions. This is a beautiful question, I'll say. Many concepts could be clear. See, while learning, what I will say, or what is very important is understanding what is electron-rich species. Always identify. See, organic is not very tough. Understand this. Organic is not very tough. You have to just identify which is electron-rich species, and which is electron deficient species. One is electron rich species, and other is electron deficient. That is what you need to identify, right? So here it is a PCl5. This is the compound. In the first case, it is this is the compound which is given over here. This is CH2OH. Okay, this is what they have on a arrow, PCl5. What is a PCl5? PCl5 is a source of Cl minus ion. Understand? See, if you want a Cl minus ion, there won't be any, this is actually reaction in which the nucleophilic substitution. This category of the reaction is a nucleophilic. Nucleophile will get substituted. Nucleophilic substitution, substitution reaction, right? PCl5 is a good source of Cl minus because there are 5 Cl group which are very much bulkier. If you want to write the structure of the PCl5, these are the 5 Cl, 1 Cl over here, 1 Cl over here. This is on the top, this is below. So all these 3 Cl are in plane and one above, one below, right? So they are very good source of, like, this bond could be broken very easily because lot of repulsion is there. There are in addition to this, there are lone pair also on this. right? So they will always repel and you will get easily Cl minus. Once you get a Cl minus, what will happen is that now Cl minus is my electron rich. How it's generated? It is generated from PCl5, right? This PCl5, this PCl5 will give me what? Cl minus. Now this is your compound. See, our mechanism is not very big. It is not a very big rocket science. CH2. OH, right? This is Cl minus. Now I am going to use the word attack, where it is going to attack or where it is going to donate its electron, where there is a deficiency of the electron. See, there are a carbon over here. These are also a carbon. This is also a carbon. This is also a carbon. But these carbons, there is a pi bond which is making this is a electron rich, not electron deficient. But here, this is a carbon. To this carbon, there is a oxygen which is connected. What is the nature of the oxygen? It is electronegative. Electronegative. Now electronegative means what? It has the tendency to pull the electron. It has the tendency to make the bond polar, means it will pull the electron of the carbon and this carbon is going to be partially positive. So where this halide is going to break, attack on this carbon only. Once this carbon attack is taking place, what's going to happen is carbon is going to form a 5 bond, which is not possible, right? So one bond should break, always the bigger bond. Okay, the longer bond is going to break. The longer bonds are easy to break. So here carbon oxygen will be a longer bond. So this is the bond which is going to break. And what compound you are going to have is final compound. What you are going to have is this CH2 Cl. That's it. So you should be writing this product here. Means after the reaction with this, it is a nucleophilic substitution reaction, and the compound what you are going to have is this, right? So next is let's do with second question. Here I will go into little depth. Slowly, I am taking you into depth of the topic. Um, please cooperate. You know, organic chemistry is like mathematics. More you solve, more you become perfect. Don't try to save your pages. Waste some pages. Okay, then only you will become perfect. I'll not say perfect, but you will develop a taste or a love for organic chemistry. This is HBr. Now, it is always electron rich to electron deficient, right? So this is the reaction which is given. So this HBr, understand role of every reagent. This HBr is a source of H plus. We'll understand this step by step since we have written the reaction. This is source of a H plus. This H plus is also known as a proton, right? So the thing is, in the mechanism part, we'll learn mechanism. This mechanism is very important. You are not asked to write a mechanism, but based on the mechanism, you can solve many questions. Okay, understand this one mechanism. CH2, CH, double bond, and a CH2. Now, this is the H plus, which is electron deficient. Now, if I keep a Br minus also, will there be a reaction? Because this is also rich, this Br minus is also rich, this benzene ring is also rich. So there won't be a reaction between this and a Br minus. But this is rich and this is electron deficient. So there will be obviously a reaction between a H plus. So HBr is a very good source of a H plus, very strong acid it is. So it dissociates to maximum extent, right? So the attack possibility, like one bond possibility, the H plus will get substituted here or H plus will get substituted over here. But in any of the case, what's going to happen is one carbon will lose its electron. Either this bond or this attack, either both the attacks will try. So I'll call this to be A and I'll call this to be B, right? So one through a A. Let's say this is A and B. I'll write both the possible products. If attack is through A, you are going to get this. CH2, CH, positive charge, and this is CH3. And if it is through B, then CH2, CH2, and CH2 plus. Now, in both the cases, there is a carbocation formation. Secondary carbocation is formed, and here it is a primary carbocation, which is more stable. Always remember that. Tertiary is always more stable. What I write is a stability of a carbocation. Stability. Understand this order. Stability of 1 minute. Huh? There is, yeah, computer processing is a bit slow. Stability of carbocation. What is the order? Tertiary is more stable than secondary, and secondary is more stable than primary. This is what the order. So who is more stable? This is more stable, and this is less stable. So whenever there is a formation of the carbocation, so carbocation, whenever there is a formation of the carbocation, uh, there is carbocation, there is possibility of, there is, understand, huh? This, there is possibility of hydride shift or methyl shift, only to increase the stability, only to increase the stability. This will take place only if there is a secondary carbocation changing to more stable. It may be a secondary, or it is coming into the resonance. If it is a primary, then it should change to secondary. Then only it is going to take place. So here, this is less stable. So reaction will not proceed in this direction. It will proceed, but very less amount of the product will be formed. So here there is a secondary carbocation, and there will be a hydride shift. Although it is remaining a secondary only, but here there is a resonance. Here there is a resonance. Something which is stabilized by resonance is always more stable. Hydride shift means what? This hydrogen will come here, and here this will form a positive, and this is CH2, CH3. So this is a hydride shift, and this is more stable. Although this is also secondary, but here it is into the conjugation pi sigma positive. This is most stable carbocation. So next is what? Br minus is going to come. Br minus is going to attack here, no? And the final product will be what? This S, no? So this is the answer for this.